Good afternoon, everybody. It's a beautiful summer's day coming up to the 21st of June, but now we got another highlight here with our speaker today, Robert Fisher, talking about a very important topic. I'm sure that everybody will be aware about that. But to introduce Robert, I want, like Chris Byrol, to say a few words.
Thanks. Yeah, it's my pleasure to introduce Robert Fisher, from the University of Massachusetts, Dartmouth, where he's a full professor and has been teaching and doing research for roughly the past 15 years. Currently, we are happy to have Robert as a visiting faculty at the HITS here in Heidelberg until the end of July with a DED fellowship. And well, initially, Robert started out his undergrad in California at Caltech, doing a Bachelor's of Science in Physics in 1994. And then he moved on to Berkeley to do his PhD thesis with Chris McKee and Richard Klein. And during his PhD, Robert worked on simulations of star formation, along with writing the necessary numerical solvers. And he then graduated in 2002 with his PhD thesis titled Single and Multiple Star Formation in Turbulent Giant Molecular Cloud Cores. And then in the postdoctoral phase at Lawrence Livermore National Laboratory, he published the first quantitative semi-analytical theory on the distribution of binary stars. And while Robert continues to work on turbulence in this context of star formation, it seems that he became increasingly interested not in the birth of stars, but the deaths, specifically for type 1As. And this particularly took place after he moved to the Flash Center in Chicago, where he carried out some of the first three-dimensional near-Chandrasekhar mass detonation simulations. Since then, he's been the PI of various observational, theoretical, and computational efforts, where he made substantial contributions to decode and understand type 1As and the role that turbulence plays in these. And just recently, Robert was awarded a NASA ATP grant to continue on this path to develop a basic theory on the physics of turbulence-driven detonation initiation in type 1A supernovae. So finally, one thing I found interesting about this publication list was in 2008, he published a publication with the title Terascale Turbulence Computation in Flash 3. And so today, roughly 15 years later, we are talking about hydrodynamical codes and simulations, many orders of magnitudes bigger and faster. And in many ways, I hope that our theoretical understanding just progressed at a fraction of this pace. And I'm very curious to hear about the progress in theoretical and observational advances on the nature of white dwarf supernovae. Thank you.
Thank you, Chris. So it's my pleasure to be here and to talk about type 1A supernovae. And I do this work with a large cast of people. And one of the best things about being a faculty member is working with those junior people, including Chris, who was in Massachusetts now almost a decade ago on a DAD. So it's sort of like the cycle of life that I'm here in Heidelberg on a DAD. So today, what I want to tell you about is the topic of type 1A supernovae. And I can tell you in very broad strokes what I'll be discussing. We'll talk, of course, at the beginning, a little bit of an introduction to type 1A supernovae. We'll talk a little bit about the observations and the theory. And then we'll talk about two channels, mergers of white dwarfs, as well as near-Chandrasekhar mass explosions of white dwarfs. When I first started in this field, the primary theme that most people had in mind is that these near-Chandrasekhar mass explosions would account for the majority of the kind of normal type 1As. We'll talk about exactly what normal means in a second, explosions. And these other guys, the mergers of white dwarfs, might be some weird objects. And what I'll try to convince you of by the end of today is that actually the situation is reversed, that near-Chandrasekhar mass explosions are probably, if anything, failed explosions. They don't completely detonate, but will partially detonate. They'll partially explode, leaving behind a remnant. And the mergers of white dwarfs may account for the majority, if not all, of normal 1As. And I'll explain why that is and why our thinking has changed on the subject over so many years. So to begin with, let's talk a little bit about observations. So first off, just why are supernovae, supernovae as a very broad class of events, important? So here are supernovae, and there are many, many reasons why they're astrophysically important. And when I say supernovae, I mean both thermonuclear supernovae that we'll be focusing on primarily in this talk, as well as core collapse supernovae. Well, for one thing, they're important because they produce gamma ray bursts. There's a certain class of supernovae, the long gamma ray bursts are associated with. These are the type 1Cs. And if you're not so familiar with these classes, don't worry. In a second, I'll break this down and remind everyone what these designations mean. But gamma ray bursts, the long gamma ray bursts, are associated with supernovae of type 1Cs. Now, in addition, supernovae often leave behind remnants. Of course, we're always familiar with neutron stars and black holes that are left behind frequently as core collapse supernovae remnants. And those will be 1bCs and type 2s. But one other interesting thing that we've learned over the last decade or so is that occasionally some thermonuclear supernovae do not completely detonate. Those are phenomenologically known as 1AXs. So white dwarfs may also sometimes be left behind as remnants. There's actually very good evidence for this now from Gaia that we'll be talking about later. In addition, supernovae enrich the ISM. They provide all kinds of nice heavy elements, as well as energizing and giving momentum back to the ISM. They are the source of cosmic rays, and they're also the source of multi-messenger signals in neutrinos, gravitational waves, and of course, lastly but not least, they're also the class of type 1A supernovae are famously known as standardizable canons. Now, let's talk a little bit about how supernovae are classified. So a broad division between type 1s and type 2 supernovae is simply based on hydrogen. If a supernovae has hydrogen, it's a type 2. If a supernovae does not have hydrogen, it's a type 1. If you go back in the literature, not actually that long ago, to like the 70s, early 80s, that was all that existed. There were just type 1s and type 2s. But it wasn't very long before people realized that some of the type 1s looked very different. So a type 1A, which we believe now to be the explosions of white dwarfs, is characterized by the presence of a silicon absorption line at around 6,100 angstroms. But in addition, there are these other type 1 events that are very, very different, the type 1Bs and Cs. And these are now known to be basically stripped envelope massive stars that explode as core collapse supernovae, essentially. And they're characterized by, in the case of 1Bs, some weak hydrogen and strong helium, 1Cs even further stripped without any helium. So those are very, very different than the 1As. Those are essentially the same core collapse mechanism as the type 2s, but they have their outer envelopes stripped. Now, in addition to the spectrum, you can also look at the light curves of these events. And this is, if you're interested in cosmology, this is especially what you hear a lot about. And I'll just talk really briefly about the light curves and how they are related to the standardizable candle of cosmology. When you look at most normal 1As, and this over here is an old survey that was carried out at Kalantololo that led to the characterization of normal events. And when you look at these events, they differ in their peak brightness by about a magnitude or so. However, when you look at their decline rate, and the decline rate is normally thought of in this way, peak brightness is at 0 here. This is time, and this is magnitude, an absolute magnitude in this case, because these are all determined from a calibrated sample that are tied to the Cepheid rung on the standard candle ladder. So these magnitudes are brighter depending on the decline rate. And this quantity, which is called delta M15, characterizes how much the light curve has declined after 15 days. So for instance, this light curve on the top, when you look at this, it's declined by about 0.7 mags after 15 days. It's all relative to peak brightness because peak brightness is about the only thing you can reasonably get a handle on because they're often not caught at the time of explosion. And especially in the old days, it was very rare to catch early events. And you can see that the two are correlated. The decline rate is correlated with the brightness. That's the so-called Phillips relation. And by this point in time, this has become quite quite an advanced art in characterizing these light curves purely in a phenomenological way. That's how cosmology is done with light curve fitters like SALT that take in the decline rate, the peak brightness, the color, and allow you to characterize the magnitudes and to build up cosmology. So that's one branch you could talk about. You could have many colloquia just on the cosmology side. We're going to be talking primarily about the fundamental physics and astrophysics of how these stars actually explode. Now, from that set of light curves, you might be led to think that type 1As are mostly about the same brightness. And this is actually one key thing is that 1As are actually quite a diverse class. And this is another set of points showing in gray the normal events. And I'm showing here absolute magnitude on the vertical scale. Remember, every 5 mags is a factor of 100, right? And then on the horizontal axis is delta M15 that we're just looking at in the B band. And just looking at this, you can see that the type 1As span quite a broad range. It's almost 5 mags in just even the normal events. And normal events, by the way, are spectroscopically normal. They're really characterized by their spectrum being similar. And in addition, there are these other types of events when you look at this set of points, these 1AXs that we talked about a moment ago. Those are the failed events. 91Ts are brighter. And so you can see that they span quite a broad range. We want to understand all of this when we understand the explosion mechanism. Now, the channels of 1As, there's a couple of channels. This is not by any means to be exhaustive. I'm just going to go through a few of the main channels and the main channels that we'll be talking about, especially today. So one way, basically, any way that you can think of to explode one of these white dwarfs, because white dwarf is sub-Chandrasekhar. If it's a sub-Chandrasekhar mass white dwarf, it's rock solid stable. You need some mechanism to blow it up. And if it's not, if nothing is born at the Chandrasekhar mass, which we'll talk about in a moment as well, so something has to happen to allow this explosion to occur. It has to have a binary system or a collision. So almost all the mechanisms involve a binary system. And that means you start with a main sequence binary. There's a common envelope phase of evolution that I'm going to not plot here that's shared in common by all these. After a common envelope phase of evolution, one way you could go is you could eventually form a carbon-oxygen white dwarf with a main sequence red giant, hydrogen donor, and that can lead to a near-Chandrasekhar mass single degenerate explosion. I'm going to try to characterize these in terms of what's left behind. In this case, if the Chandrasekhar mass white dwarf blows up completely, you would be left behind with just the companion, right? But we're also going to be talking about how, in some cases, this channel may also not lead to the complete detonation of the primary. It may lead to a failed detonation. So in that case, you might actually have both stars surviving. We'll see some evidence for that in just a minute. Now, in addition, you can have a completely separate channel. You can have the two stars going off in a different branch, forming a carbon-oxygen white dwarf with a giant, and then a second common envelope phase of evolution where you have two carbon-oxygen white dwarfs. More massive carbon-oxygen white dwarfs are almost all carbon-oxygen, and perhaps those two stars, those two white dwarfs, come together by gravitational wave radiation and eventually merge, and they could explode. That kind of explosion, this is a kind of what I'd call maybe a classic double degenerate channel, would leave behind nothing, no stars, nothing, just the explosion itself. In addition, this is actually what we'll be focusing on today. You may not ever, for most events at least, you may not ever get a complete merger. And what I mean by that is that stars, as they evolve to form white dwarfs, star like about a mass of our sun or more, will have on its surface, just by ordinary stellar evolution, left over a small amount of helium. And about 1 solar mass, carbon, oxygen, white dwarf, that we're talking about maybe a few thousandths to a few hundredths of a solar mass of helium. And that helium on the surface of the donor white dwarf may accrete onto the primary white dwarf. And helium is a lot easier fuel to burn than carbon. So you can have a helium transfer onto the surface of the primary, leading to a double detonation, meaning the helium detonates and then the carbon oxygen detonates. One possibility here is that primary detonates, it's gone, and then you would be left with just the secondary, the second white dwarf ejected from that system. And we'll see another interesting possibility where maybe even in some cases, even the secondary explodes. So it's not just a double detonation, but it's really a quadruple detonation. So Gaia has been really transformative for this field. There have been 10 hypervelocity white dwarfs which have been discovered in Gaia. These have really been transformative because for years and years, people have looked for those stars among other kinds of evidence from type 1a supernovae, and basically every time it's turned up no dice, nothing, right? You can look at the remnants that are known in the galaxy and the LMC. There are no companions, X-companions that are known. You can look in pre-explosion images for the nearest events that have been seen, like 2011 FE or 2014 J. You never see anything in the pre-explosion image. You never see anything in the post-explosion image. You never see any H alpha. You never hardly ever see any X-ray signature. So there's hardly any evidence to point to. There's lots of limits in the literature, but Gaia really transformed the field because for the first time, there's very, very strong evidence for the companion or X-companion in the system. So 7 of those hypervelocity white dwarfs are thought to be the donors in that last channel that we were just talking about, where the primary white dwarf explodes, second white dwarf gets shot out, and these are some of the fastest stars in the galaxy, 1,000 to 2,000 kilometers per second. One of those, in the first paper that was published by Ken Shen et al. A few years ago, actually traces back to a remnant in the galaxy. That was called D62. In addition, there's another 3 hypervelocity white dwarfs, which are thought to be the leftover near-Chandrasekhar mass white dwarfs in a Chandrasekhar mass explosion. They look a little bit different. They have different velocities. Their abundances on the surface are different. And there are 3 of those as well. When you look at the spectra of those hypervelocity white dwarfs, they look pretty weird. So what I'm showing is a figure from Shen's paper. At the top is a DA and a DB white dwarf. A DA is basically a hydrogen atmosphere white dwarf. DB is a helium atmosphere white dwarf. Almost all your sort of garden variety white dwarfs will look like this. The 3 next set of spectra are polluted spectra, weird looking white dwarfs in the galaxy. And the bottom ones are the D6s, the hypervelocity white dwarf candidates. And as far as I know, I think a detailed analysis in the spectrum is not still out. It's still in the works. But what you can tell just from this is that these are not normal looking DAs or DBs. These are pretty weird looking objects. So let's talk a little bit about the theory as well. So there is a very nice, elegant theory about the masses of white dwarfs and the energetics. I'll just step us through. Some of this goes back to Landau and Chandrasekhar. And when you have a white dwarf, the white dwarf has a very high density. And the interior, the electrons are not just degenerate, they're relativistically degenerate. So you can come up with a very simple estimate for the energy, the Fermi energy of those electrons from the Heidelberg uncertainty principle. Just saying, and what we're going to say here is that these electrons have the most energy you can possibly have. They're all ultra relativistic. Just forget they have any mass whatsoever. Their energy is just their momentum times the speed of light. So you can estimate what that Fermi energy is. The space each electron occupies is basically the number density of electrons to the 1/3 power. And if you just cast that in terms of the number of electrons you have in the white dwarf and the radius, it scales exactly this way. And just a very simple dimensional analysis. We're not going to worry about the prefactors here. Just add in the gravitational energy for the whole star with all the electrons. So the total energy is the number of electrons you have times the Fermi energy and the gravitational energy added up. And when you do that, you find something pretty interesting. You find that the Fermi energy of all those electrons and the gravitational energy scale in exactly the same way. They scale both as 1 over r. The star would want to minimize its energy. So ordinarily, when you do this kind of analysis in stellar structure, you'll find that the star finds a radius that will minimize its energy. But this is a problem here because these both scale as 1 over r. So Landau had a kind of clever argument here. He said, well, if this energy, the total energy, were positive, you'd want to minimize your energy, which would mean you'd want to expand. But if you expanded, eventually the star would expand to such an extent it would no longer be degenerate, would not be relativistic. The whole assumption of the model breaks down. And if it were negative, well, if it were negative, it would want to collapse down to as small a radius as you would want. So both of those don't give you a consistent solution. The only solution is the energy has to be 0. If you're familiar with the polytrope, theory of polytropes, you know that an n equals 3 polytrope, which is a ultra-relativistic case, has a total energy of 0. So this is another way of saying total energy has to be 0. So you can solve then for the mass once you set it to 0. And that gives you the Chandrasekhar mass to within, factor order unity. It's also going to be the maximum mass. Why the maximum mass? Because we assumed that these electrons are as energetic as they could possibly be. You can't get any more oomph out of this system. So this is a characteristic mass, which is also the maximum mass. And it scales in a very fundamental way. It can be written this way, which you can see is basically just a combination of two things. It's a very, very big number, which is the ratio of the Planck mass to the baryon mass times the Planck mass itself. This very big number, we actually have a very deep understanding of that as well, because we know what the energy of protons is, or what the rest mass is from a very deep theory, from QCD. So when you look at QCD sets an energy scale, which is about 1 GeV. And why is that? It's because the strong force is only strong at low energies. If you look at higher energies, of course, strong force is not strong. It's actually quite weak. So the characteristic energies of all the low mass baryons and mesons is always about 1 GeV. So this number, the Planck mass of the baryon mass, is about 10 to the 19. 10 to the 19 squared is 10 to the 38. Planck mass is about 10 to the minus 5 grams. So this is about solar mass, right? It's a very kind of first principles, elegant way of understanding this really important result, one of the most beautiful results in physics. Chandrasekhar also wrote it down in a more sort of comprehensive way. And although he first got the prefactor here incorrect as well. So I'm giving you the sort of modern mass. So the energy that would be released if you could burn all of that mass, carbon, oxygen, to nuclear statistical equilibrium, which is nickel 56 at this kind of conditions, is about 1 MeV per baryon. That gives you around 2 times 10 to the 51 erg. Sometimes that unit of 51 erg is named a beta after Hans Bethe. And if you subtract off the binding energy, that's about 10 to the 51 erg, which gives you a characteristic velocity of around 10 to the 4 kilometers per second. What's more is that that primary isotope that we're talking about, nickel 56, is radioactive. So the light curve is powered by that radioactivity. It's powered by the decay of nickel 56 to cobalt 56 to iron 56, which is about 6 MeVs, not per baryon now, but per nucleus, over a time scale of about 80 days. And when you work that out, it's total energy, a total power of around 10 to the 10 solar luminosities. 10 to the 10 solar luminosities, remembering that the sun is about magnitude 5, means that this is about magnitude minus 20. So that, if you remember the light curves we were looking at, those are basically on the bright side of what we were seeing. Why on the bright side? Because we assumed in this really simple model that all of the star gets combusted and turned into nickel 56 That's not going to be the case in actuality. You're always going to burn a little bit less. But after I tell you all this about this beautiful theory about Chandrasekhar mass explosions, it's also very important to note that you can take a sub-Chandrasekhar white dwarf. If you can actually detonate that, you get very similar energetics. So that leads us to the next part, right, which is about white dwarf mergers. So white dwarf mergers, there are some people in the field that you kind of really can admire. Almost every paper they have is really insightful. Stan Woosley had a paper some years ago where he asked this almost rhetorical question, but was actually deeply insightful. And he said, if a common starting point, namely that you have all these white dwarfs nearly the same mass as Chandrasekhar mass, is the explanation why type 1As have nearly the same brightness, then why are they diverse? What is the reason? If you thought about Chandrasekhar mass explosions, maybe that would lead you somewhere else. But the modern thinking about this, or at least one interpretation of this, is that the explanation is different. If I explode not Chandrasekhar mass white dwarfs, but sub-Chandrasekhar mass white dwarfs, I can account for the diversity of all those events that we were looking at earlier. This is a non-trivial result that Ken Shen showed a couple of years ago. It's non-trivial because to calculate these synthetic light curves just by explosions of bare carbon-oxygen white dwarfs, he had to use non-local thermodynamic equilibrium rate of transfer. That was important to get this accurate. But what you can see is that essentially the range of the brightest events to the dimmest events, the most slow decliners to the most rapid decliners, is explained simply by the mass of the white dwarf. So if you can explode a range of white dwarfs from 0.85 solar masses to 1.1, which is all towards the very heavy end of carbon-oxygen white dwarfs, you can account for the entire range of diversity of type 1As. So can you do that? So that will lead us into understanding simulations of this. Let me talk a little bit about how you simulate these. When you think about these simulations, the most important to think about the type 1As is that they are very broad range of scales, or very multi-scale. The range of scales I'm showing here is a log scale in centimeters, from everything from the white dwarf radius to free expansion. When you simulate, you can simulate down to some grid resolution I'm showing you a typical value of. But then there are these other scales. This is a common theme in astrophysics, that there are scales you can never access. There's a scale where turbulence is dissipated way down in the Kolmogorov scale, which is very small because of the degenerate conditions inside the white dwarf. And there's also burning conditions that lead to subsonic flames and detonations. All of those are unresolved. And if you think about this, the range of scales I'm showing here is over 15 decks. If you talk about a Hubble volume, you're talking about like the same equivalent range of scales that you would be talking about, everything from the Hubble volume down to solar systems, about 1 AU. So it's a huge range of scales. You'll never be able to resolve these. The first set of simulations I'm showing you, what is done is that you resolve some scales, and the other scales, you have to artificially thicken flames and artificially thicken the detonations to capture them on the mesh. That's essentially what we'll be doing for this first set of simulations. At the end of the talk, I'll talk a little about some other steps we're taking towards improving those kinds of conditions. So these two white dwarfs coming together, this is sometimes called a D6 scenario. It's a double detonation, but it's also sometimes called a dynamically driven double degenerate double detonation because they're coming from two white dwarfs. So the initial conditions are very critical, and they're very challenging to get correct. So what has to happen is you need to follow the evolution of a binary system, and this evolution occurs over many, many years, in fact. And this in reality would be driven by gravitational wave radiation. It's impossible to do this on a computer, so you have to sort of artificially expedite this process by putting artificial torques and damps of sinks of energy into the system. And through this, you can form a binary system. And what I'm showing here is that process towards the end after the artificial acceleration has taken place. But it's intrinsically three-dimensional. The accretion stream is intrinsically three-dimensional. The rotation is intrinsically three-dimensional. you really can't model this process in 1D or even 2D. So I'm going to show you first a couple of simulations that we had at the state of affairs of a couple of years ago. And I think we've learned a lot since then. And so my position, in fact, has changed even in the last year or so on these. But a couple of years ago, we set up a simulation with one set of masses, with solar mass and a 0.6 solar mass white dwarf, with a thin layer, relatively thin layer of 0.01 solar masses of helium on the surface of each, and another in the accretion stream. And this is kind of what this looks like. When you simulate this, this is done in Flash with adaptive mesh refinement. And here I'm showing you the density. And what you can see is that in this simulation, we do get the helium detonation on the surface, but we did not see a core detonation. There was no detonation of the underlying core. So this would not be a type 1A. There's not enough energy that's released in that explosion. The temperature slices show what's going on. You're getting an initial ignition of one spot, and then a second ignition in the helium layer, but it's on the opposite side. The core itself never experiences a detonation. A lot of the older literature, when people are studying double detonations, is often done in a highly simplified geometry. So even in 1D, if you have a 1D double detonation, you have a spherically converging detonation front, and it's almost inevitable that the core will ignite under such a condition. But in a realistic three-dimensional geometry, it's not as assured. When you look at the helium, it's also very interesting. This is showing helium abundance, and the helium abundance shows that you ignite the surface, you burn up the helium on the surface, and what's more is there's only a finite reservoir of helium in that system. So that single detonation on the surface has combusted something like half of the helium in the system. If you waited around, you might get another secondary event, but there's only so many chances you would have of getting a successful explosion. Now, at the same time, Rudiger Packmore has simulated this process, and he's done this very carefully as well. Slightly different set of masses, slightly different helium masses, and he finds here, if you follow this through, a successful detonation of the primary. And the second white dwarf survives the explosion in this case, right? You can see this here, right? If you look carefully, first the primary gets detonated, the secondary a little bit later survives. So this might be an explanation for one of the Gaia hypervelocity white dwarfs that's been seen. But one puzzle with the Gaia hypervelocity white dwarfs is that there's not enough of them. There are, by some simple accounting, maybe only about 1 to a few % of the total number of sources that you should see if this mechanism accounts for everything. So Rudiger did another calculation that I thought was very interesting, which in this simulation, you get the detonation of the primary, but then you see there's also the funnel, the helium accretion stream starts to burn. And in this case, there's also a detonation of the secondary. So both the primary and the secondary ignite. And Ken Shen has just recently written a paper that just came out a couple of weeks ago that kind of provides some rationale for this, and essentially that most white dwarfs will have enough helium on their surface to allow them to detonate, just by virtue of the fact that they have this helium on their surface, enough of it there. Only the most massive white dwarfs will have thinner helium layers and may survive and may be seen as a hypervelocity white dwarf. So one of the amazing things about computational astrophysics, it's incredibly challenging to resolve all these scales. You might say, well, it's hopeless. We can never resolve down to the Kolmogorov scale or anything like it. But what we can do is we can come up with very interesting predictions that could be true. So the question really is this really true? And we're working with Rudiger, and actually, when we have the same initial conditions with Arepo and Flash, we have almost the same outcomes now. This shows a little bit earlier in this set of simulations, not quite to detonation, but you can see even down to fine-grained features in the accretion stream and the instabilities, they're almost all in complete agreement. So I think the initial condition generation is very important, and I think that's probably a key difference between our previous calculations, which were done with SPH as an initial condition. Here, everything is basically from beginning to end in Arepo or in Flash. So how can we test this? I'll give you just 2 probes that we can use to test this. One is that titanium-44, which is a radioactive isotope, is produced in abundance when you have incomplete helium burning, like on the surface of these white dwarfs. And titanium-44 is radioactive with quite a long half-life of around 60 years. So it's long-lived enough that it can be seen in the galactic remnants. And already the simulations are at a level where they're kind of at the limit of what has not been seen. There are upper limits for the historic remnants like Kepler and Tycho that have been seen in the galaxy. And what's more is that there's a pretty big discrepancy or big deviation between just a double degenerate merger where you have the helium burning on the surface and the explosion of a Chandrasekhar mass white dwarf. So that may be a key distinguishing characteristic between these two, is the amount of titanium-44. There are future instruments, COSI and AMIGO. AMIGO is an all-sky survey that will push these limits down to 10⁻⁴ solar masses of helium in the galactic remnants. This could potentially probe whether these events occur or not. In addition, when you look in the nebular phase, that is after the photosphere has basically receded all the way into the core of the supernovae, typically like very many months or years even after the explosion, you can peer directly through the whole explosion. Those nebular spectra allow you to determine what's going on inside the white dwarf, what went on inside the white dwarf explosion. And for instance, if you have a thick shell, a uniform sphere will produce a line feature like this that's shown up here. If you cut out the interior of the uniform sphere, you get these so-called flat-topped profiles. And this is what it would look like in the synthetic spectra. And JWST is gathering these now. The spectra are exquisite in infrared, never been seen before. And so this will be seen. And I think that it's hard to imagine that such an asymmetric explosion with the explosion of two white dwarfs would not produce something here that could not be probed. So the D6 summary, initial conditions are very important. Observational constraint on titanium-44 is important, and nebular phase spectra will help probe those outcomes. So lastly, I want to tie into the near-Chandrasekhar mass scenario. This classic scenario, so if the normal 1As are the white dwarfs that merge together, what exactly are these near-Chandrasekhar mass white dwarfs? And this turns out to be, in many ways, a lot harder of a problem. Near-Chandrasekhar mass white dwarf fundamentally explodes in a different way because you build up to the Chandrasekhar mass by the accretion from a companion, and the white dwarf has a radius-mass relationship that the radius shrinks as the mass increases. So the core undergoes nuclear burning. It revives itself at the last century or so of its life. And it looks something like this on the interior. The central temperature is almost 10 to the 9 Kelvin. Central density is around 2 times 10 to the 9 grams per cubic centimeter. And there's an interior core which is convective. And eventually the convection leads to the ignition of a flame. What does it look like? Well, this is a simulation we did a long time ago, but shows this quite beautifully. You have a flame bubble which ignites inside the core of the Chandrasekhar mass white dwarf. And this is a simplified setup where you just have a flame channel. You just have basically a stratified atmosphere inside the white dwarf, the core of the white dwarf, and you ignite in the core so you can have a very, very high resolution. The flame rises because it's buoyant. The ash is less dense than the surrounding medium. And after a while, it starts to develop instabilities. There's both Rayleigh-Taylor and Kelvin-Helmholtz instabilities. That leads to enhancement of the surface area of the flame. The enhancement of surface area means it burns more rapidly and may eventually undergo a detonation. That's fundamentally different than the burning on the outside of a white dwarf, because the burning on the outside of the white dwarf, the flame speed is so low that essentially the burning is not occurring as a flame, it's just occurring in a so-called distributed phase. And there's several proposed mechanisms here. They all start with flame ignition. Maybe you have a pure deflagration, maybe you transition to a DDT, maybe you even have some other kind of scenario where the bubble bursts out over the surface and wraps around and detonates. But really, all of this hinges on the question of what happens to this ash, this bubble, as it rises. Can it actually somehow accelerate its burning to be rapid enough to detonate or not? So there are a couple of characteristic speeds that you have in combustion. Now, I'll just talk about this very briefly, kind of to remind everyone what this looks like. If I plot on the vertical axis pressure and the horizontal axis specific density, which is basically just 1 over density, you have a Hugoniot shown here for the combusted state. The 1-1 state here, I'm showing this ratio to the pre-combusted state. So 1-1 is that pre-combusted state with the same pressure as you had pre-front and the same density that you had pre-front. So this set of points along the Hugoniot are exactly what you'd get just by the addition of enthalpy from that state. And there are a set of lines here, the so-called Rayleigh lines, that designate constant velocity. So there are 2 specific points on this curve, which are one of which up here on the detonation branch, which indicates a detonation speed. And then there's another point on the other branch, which is subsonic, which is a deflagration speed. And these 2 special points, they're called the Chapman-Jiguet speeds. There's one point up here, which is a so-called detonation speed. And if you connect that to experiments, it agrees very nicely with experiments, even if this very simple theory that I'm showing you here, which is basically treating the detonation front as just an infinitely thin front, is maybe only a beginning point. There's a more thorough theory of this that's due to Zeldovich and others that really accounts for how these arise. But then there's a second speed down here, which is the Chapman-Jiguet deflagration speed. And that's a maximum speed. If you do a stability analysis, you can prove that in a one-dimensional laminar flame that this is the fastest speed a laminar flame can have. But that kind of raises the question, what happens or what would happen if you push the flame beyond that limit? That can happen in a turbulent flame. You can push it beyond that in a non-steady flame. And my collaborator, Alexei Polandenko, did a nice set of simulations on this for both terrestrial combustion as well as astrophysical combustion. This shows that flame surface. And now we're looking at this on a very, very small scale, right? This is here in centimeters, I believe. So a very, very small scale. This flame surface, as it moves, enhances its flame surface area. As the surface area enhances, it burns faster. As it burns faster, it runs away. And you'll see at some point, it actually leads to a detonation. And that happens exactly when the Chapman-Jiguet deflagration speed is exceeded. Now, there's also a very simple understanding of this theoretically. If I take a little flame surface that's shown here, and I try to inject energy into it faster than the sound crossing time in the ash. Well, you think about that, right? For this flame to try to adjust its burning rate, it has to adjust its area. It has to increase its area to have a higher burning rate. So for it to respond to the injection of energy at such a rapid speed, it has to move, has to increase its area. But at some point, if the energy injection rate is faster than the sound crossing time, it cannot do this in any subsonic way. It has to lead to a pressure development, overpressure, and a detonation. So when this condition is exceeded, you can show that actually that's a one-to-one correspondence between the flame speed exceeding the Chapman-Jiguet deflagration speed and this sonic burning rate. So they're intrinsically unstable. They lead to detonations. So we've done the first global three-dimensional simulations, putting this criterion into three-dimensional simulations. We're very excited to do this. We thought we finally have honed in on the answer to this classic problem. I'll just sketch out a little bit of the methodology. The methodology is a little bit involved, but let me just give you a little flavor of this, right? So the flame will be wrinkled, right? You have to sort of model what's going on beneath the scale of the grid. Remember how we were talking about that earlier? You can't resolve the flame. So how do you do this? Well, you can model it because the flame surface will be wrinkled. Wrinkled on what scale? Well, turbulence cascades downward, and it cascades downward to the point where the flame speed, the laminar flame speed, that is just the speed that the flame would progress normally in the absence of any wrinkles whatsoever, would be about the same as the turbulent velocity on that scale. If the turbulent velocity balances that flame speed, then the flame speed can wrinkle out the surface. It can erase those wrinkles on that scale. And beneath that scale, the turbulent velocity will be lesser, and so the flame will be smooth. That sets the kind of wrinkling scale. And if you assume that the turbulent cascade is cosmograph above that scale, then you can also express the turbulent velocity on some larger scale, which I've written here as L, sometimes referred to as something like the integral scale, and that sets the wrinkling scale. The wrinkling scale is this scale, which is some scale that you can put in the grid that you can calculate on, the integral scale, as well as the turbulent fluctuations on that scale that you can resolve. And then the flame speed is something you can compute. So you can compute that wrinkle scale, and you can then model the burning rate that occurs on the unresolved scales. So we did this, we put it in to global three-dimensional simulations of Chandrasekhar mass explosions. Lo and behold, the white dwarfs all explode very, very soon, very rapidly. So here's a case with one bubble, the single bubble, and what I'm showing here is on the blue scale is just the density of the background white dwarf, and on this other scale is the sort of characteristic length scale in which we measure everything, which is just a few grid scales compared to the Chapman-Jagay scale. That is the scale in which the flame would exceed the Chapman-Jagay deflagration speed, would lead to a detonation. And you see, we're showing it at this point, but already by this point, the Chapman-Jagay length scale is already greatly exceeded, even at this very early point for a single bubble ignition. The question of ignition is somewhat of an unsolved problem as well. So we said maybe, well, if we put in a few ignition points, that's what people often do when they want to get more burning in one of these models, maybe then this thing will fail to detonate, or at least take longer to detonate. And actually, it doesn't really change the outcome very much at all, whether you put in one bubble or multiple bubbles. The reason is because whether you have one bubble or multiple bubbles, there's always a first sort of buoyant part of that ash that just rises above the rest of the background, and itself will lead to a detonation very early. So is this really the outcome? Basically, I've given you a lot of reasons to think that near-Chandrasekhar mass explosions should often fail, because we see these hypervelocity white dwarfs. That wouldn't happen if they all detonate. What's more, we've looked at a galactic 1A remnant called 3C397. It's one of the weirdest remnants in the galaxy because it has such a high level of iron group elements. It's probably our best galactic remnant candidate for near-Chandrasekhar mass explosion. And really, you can only understand the X-ray observations that from which you can derive abundances if you explode a Chandrasekhar mass white dwarf. And what's more is we had a spatially resolved set of observations that were carried out by my colleagues in Japan with XMM Newton, and it revealed a very weird structure. There's a lot of modeled to be neutronized material, which is very rich in iron group elements, which are in clumps at the outermost portions of this supernova. That kind of material, this kind of iron group elements, can only be formed in the core of the white dwarf when it explodes. So how does this material find its way to the outer limb of the explosion? So we modeled this. This is a paper we have submitted. It should be accepted hopefully this week or so, of 3C397, comparing detonations and pure deflagrations. And what I'm showing here is slice plots of the outcomes with the density on the background, and the points here are computed points where we compute the nucleosynthetic yields, showing the ratio of chromium to iron, and the size of the points shows the abundances as well. The larger the points, the higher that ratio. And there's two things you can see here. One is that a pure detonation, or a DDT, I should say, erases any kind of signature that you would have of clumpiness whatsoever. the greatest neutralization occurs in the core, and it trails off from there. A pure deflagration, on the other hand, does not forget where it came from. You have this deflagration with all those instabilities, and those instabilities push their way to the outer edge of the white dwarf and are seen in the models. So the inference is that 3C397 was very likely a pure deflagration and not a DDT. So why is this? Why is there this discrepancy? So at this point, I'm going to leave you with an idea, more of a conjecture at this point than a solid proof, but I think maybe part of the story. And the question is really, we said that to detonate, you need to have fast burning. In a white dwarf, where the flame speed is dropping off as you go outside to the outer edge of the white dwarf, it's dropping off because the density is dropping off. It's dropping off like a rock. And that means the flame will naturally fold to very small scales, which means that the DDT mechanism naturally predicts you get a lot of burning. So the question really boils down to what ultimately limits the flame speed. If it's not the flame, what is it? Well, think about this. If I take a piece of ash and imagine that there's a magnetic field in addition to just the hydrodynamics, and I imagine I take a field line that follows the surface of the ash over here, and there's a turbulent eddy, right? So the turbulent eddy will tend to wrap up that ash, and what it will do is it necessarily brings together field lines of opposite alignment through this stretching and shearing motion. You can see here, I'm kind of illustrating this. This is actually from a paper that Shekhar and Cowley wrote a few years ago. There's a scale on which turbulence will naturally push those two field lines to be very, very close to one another. That's called the, just called the reversal scale. And if that scale of reversal is set by some process, like for instance, people talk about something called the tearing mode. You can have you can have a resistivity, ohmic resistivity, but ohmic resistivity is quite slow. Tearing mode is quite fast, provided that this so-called Lundquist number is essentially just the ratio of the diffusion timescale to the Alfvén timescale, which is ginormous for the core of a white dwarf because the resistivity is tremendously small. The magnetic Reynolds number is also tremendously huge. So what happens is if that reversal scale exceeds the folding scale, then the flame cannot fold down to that small scale that you would predict. It has to basically be limited by reconnection. And that will happen if this condition is met. The reversal scale is very naturally related to the magnetic Reynolds number. And from this expression, you can see that the flame folding scale is incredibly sensitive to the flame speed, but the reversal scale is quite insensitive as the -1/3 power. So it's inevitable that the flame loses. So when you plot out the ratio of those two quantities of the reversal scale to the fold scale versus density for just some kind of typical velocity, there's only kind of one free parameter in this prescription, which is the kind of turbulent velocity you would have one of these flames, about 1,000 kilometers per second, that you have a natural transition from this flame regulated regime to a reconnection or field regulated regime. And at that point, the surface can no longer grow so rapidly and may be naturally limited. And another interesting thing to point out here is that this is independent of the magnetic field. So you don't need to amplify the field up to some really ginormous value. It's independent of the magnetic field. It's simply a question of the length scales involved. So the flame speed may be ultimately limited by tearing or reconnection beneath some scale. It would be very challenging to do these kinds of simulations, but I think it's beginning to become possible, at least to model this within a restricted range and to prove that this could actually happen. Okay, so key conclusions to wrap up. Ongoing repo and flash simulations seem to suggest that the scenario that we talked about earlier, the D6 scenario, could be a robust mechanism for the origin of normal 1As. And occasionally they may lead to quadruple detonations. I think it's a bold prediction, but I think it's a prediction that's worth testing. It can be seen in the titanium-44 and the nebular spectra. And the near-Chandrasekhar mass scenario, we have a first principles mechanism that's been incorporated into three-dimensional simulations for the first time. We have those initial hydrodynamic simulations, which I think sort of invariably will produce a very prompt detonation, but it may be that ultimately other processes involving the magnetic field, including reconnection, will put a natural brake on the flame speed and will demonstrate that those should instead not detonate, but mostly fail to detonate and produce 1AXs. That's it. Thank you very much.
Thank you, Robert, for a fantastically intuitive introduction and large dynamic range, both in your explanations as well as the calculations you present. Thank you. I'm sure there will be questions, so I'll start with the hall. Is there anybody who wants to kick off here? If I may then just interject. I mean, you are looking at these detailed calculations with the transition deprivation to detonation. I mean, is there any observable effects there in terms of the turbulence generated in terms of the ejector and the burning products that could be, you might be able to make predictions for spectra, get into it like that? Is there that feasible?
Yeah, absolutely. All those things are true, right? So especially, I think I have one sort of slide that shows a little bit of that. You can predict, of course, not just the hydrodynamics of the explosion, but you can predict the isotopes that come out of that explosion. This is the first step of that process. So what happens is you put in the models, you put in a whole bunch of tracer particles on which you can compute very detailed nucleosynthetic yields. For instance, in this case, that model that we were showing earlier looks like this. When you plot it in three-dimensional space, you get this core, which is mostly stable iron group elements and surrounded by nickel 56. Yeah. And then the next stage of that, you would be able to predict the spectra. Now, the thing about these sorts of events is that people have known for a long time that if you put in too prompt of an explosion, like that's happened here, you tend to produce overluminous events.
Right.
So that's not necessarily in this context a bad thing. And if you don't believe that Chandrasekhar mass explosions need to account for everything. So that is potentially an explanation.
So you're saying that actually can contribute to not a huge range of luminosities counteracting this, you know, you've got less material, but it's burning. You get more fraction of these products produced. So it's a sort of compensatory thing that's acting to make the luminosities of the population of these supernovae more, you know, less scattered.
Yeah, I think. Well, I think the key thing is like, if you have another explanation for normal 1As, you don't need to fit this set of events into like a square peg into a round hole. It could be, you know, just an overluminous event, but still you'd be left with a conundrum there because 1AXs are very prevalent. They turn out to be something like a third of all 1As in a complete sample. So maybe once in a while they could detonate, but I think they must frequently not detonate to account for the rate of 1AXs that is seen.
Okay, interesting. So Ralph has a question.
Thank you, Robert. This was super interesting and very, very nicely didactically presented. I'm still trying to catch up on the last point you mentioned, the turbulent reconnection. So as I understand, you will generate the turbulence by these expansion of these highly structured fractal flame, it the magnetic field, and then you have reconnection. So far, so good. But I'm a bit puzzled why the reconnection should change the dynamics of the flame by a lot, because it cannot.
So that's a good question. So the question is, if the magnetic field is not dominant energy, then how could this work? I think it's mostly in the sense that the hydrodynamic prediction is that that folding scale really is going down to extremely small scales. So anything that can change the surface of the flame and the area enhancement would arrest that development of enhanced area.
So why would the flame care so much about the magnetic field structure if it is amplifying it and you're still pushing kinetic energy from the flame, from the expansion into the magnetic sector? I think the back reaction should not be so dominant, I would guess.
The back reaction of the magnetic field onto the hydrodynamic flow, right? I see what you're saying. That's a good question. I think well, the reconnection that as it occurs, right, would lead to would take some of these highly stretched out pieces of the surface and would reconnect them into little plasmoids and flux ropes. Maybe that's not itself, the rearrangement of the area may not actually be a huge change of energy, but in terms of the flame surface, that would change the dynamics of the flame.
Okay. I should read that.
Okay, that's something to be discussed maybe later, maybe over dinner. And we do have a question from the online audience, so I read it out from Nicole Reindl to us all. Can you say something about the progenitors for the D6 scenario? What would be their properties and how many are expected to be detectable? Surely more than D6 does. So this is the question.
The properties of the ejected stars,
Yeah.
the D6. So, so it's a good question. So the ejected stars, because the shock has hit them, they will be heated up. They will have the products of the burning from that detonation front that would hit the surface. So pollution, a weird thermal structure. So when you see the D6 object.
Oh, wait a minute, the interjection here.
Sure.
So Nicole's saying, no, she doesn't mean the progenitors, not the D. She means the progenitors, not the D6 stars.
I see, the progenitors. So the progenitors, so that's a good question. The progenitors have to be basically massive enough that they can detonate and produce a 1A. So there will be somewhere in this range of like 0.8 to 1.1 solar masses. They need a little bit of helium probably on the surface, depending on the amount of mass that they can be provided from the donor as well.
Okay. There's one more question here from Mikhail Zacharias. If I may ask a very simple question, why do some white dwarf go nova while some go supernova?
Yeah.
Well, I think you had that in your introduction, but
Yeah, well, we maybe just briefly touched
Yeah.
on that, but that's one long-standing debate is that as in the single degenerate channel, whether if you have a hydrogen donor, that hydrogen donor may have a series of novae over a long time span. And the question is whether those novae actually accumulate in mass or not, whether they lose mass. Observationally, there are seen to be some white dwarfs in such systems that actually seem to be close to the Chandrasekhar mass. So observationally, it seems that it's possible to build up a star to nearly the Chandrasekhar mass. But theoretically, it's quite a challenge to explain them because there's only a narrow range of accretion rates that this is allowed.
Okay, well, thanks a lot, Mikhail replies. Okay, so it's nice to get the audience online involved. Let's just round off with one more question from the audience here.
Yeah, thanks, Robert, for a very interesting talk. I have a question to what you said on titanium 5044, which you mentioned is a signature of the helium-ignited double detonation explosion mechanism of behind the type 1a supernova. So how does it actually, can you perhaps comment on how titanium 44 is actually being formed and when and in what burning reaction chain? So that's the first question. And second question is, since you make the case that the normal type 1As are explained by the double detonation scenario, which type 1A supernova explosion types that you mentioned in one of the beginning graphs where you had the magnitude versus delta M would be explained by deflagrations?
Mm-hmm. So very good, two questions, right? So titanium 44 is produced by incomplete burning on the surface of the white dwarf. So if you have helium, the helium undergoes explosive burning. Things want to move towards nuclear statistical equilibrium, want to move towards the iron group, but the time scales are much too long for that kind of burning on the surface of a white dwarf. So you don't tend to produce iron group elements, you tend to produce sort of intermediate mass elements and products like titanium 44. It's essentially how it occurs. In a Chandrasekhar mass explosion, it's a little bit different. It does occur through other burning in the core, and so you tend to produce a lot less of it. On the second question, where are the failed events, right? Let's go back to our slide at the beginning here. So you remember that the gray points are the normal points, right? But I also showed you these points down here, including there's one point way down here. Those are labeled as 1AXs. 1AXs, observationally, these are very subluminous events. And theoretically, they're connected to those failed detonations. It's a very natural explanation. When you look at the energetics, when you look at the synthetic spectra, when you look at the light curves from a failed detonation, it's very closely aligned with the predictions of those failed detonations and account for the 1AXs. And you can see that whereas the normal events follow a very tight relationship, that's why they're useful for cosmology, these 1AXs are all over the map. They're a very diverse class. Part of that is probably just the fact that if it is a pure deflagration, they're not very spherical. They eject ash in all kinds of different directions, but probably also as a class, they don't produce nearly the same kind of energetics.
How about the 1991 T-like?
The 91 T-likes are up here, right? So those are the ones that are the most luminous. Then there's a bit of a debate over this, whether they constitute a different class of events or not. You can maybe get close to that with some of these more massive white dwarfs that are seen. If a Chandrasekhar mass white dwarf were to detonate like what we're talking about earlier, it could also possibly account for those as well.
Okay. So I think we're just to the point to wrap up now. Before we thank Robert again, I'd like just to, if I may, make a little announcement about next week's colloquium. That's it. So next week's colloquium will be given by Sergei Kopeskov from Potsdam, and we're going on to somewhat onto looking at towards the structure of the Milky Way from a theoretical observation point of view. There is some, let me give a pre-word of warning, there is some debate about whether we move the location of this colloquium from Philosophenweg 12 due to other events happening that day. So stay tuned for an announcement by email on that potentially next week. And then the final slide, I just go one on. Can I go further? Yes. Tonight, 18:30, there's plenty of places free, I'm told, for dinner at Safarino. So please contact Chris here if you want to join us for dinner. So once again, Robert, thank you very much for that fantastic, informative colloquium on this such important topic. I must say, it's amazing to see such progress and insight on such an important thing. Thank you very much indeed.
Thank you.